OpenAI introduced a new generation of AI reasoning models called O3, which the company claims surpasses O1 and all previous models in terms of advancement. The improvements seem to stem from scaling up the compute resources used during the test phase, a concept discussed last month. However, OpenAI also mentions that a new safety approach was applied in training its O-series models. In addition, OpenAI released new research on a concept known as deliberative alignment, describing their latest method for ensuring that AI reasoning models remain in alignment with the ethical values of their human developers. This approach was used to guide O1 in considering OpenAI's safety policies during the inference phase, which occurs after a user submits their prompt. What is deliberative alignment? Deliberative alignment is an approach in which language models are trained not simply to follow predefined rules, but to actively reason about user queries and align their responses with ethical and safety standards. Rather than mechanically adhering to a fixed set of instructions, models trained with this method are taught to consciously analyze queries and generate responses based on a deeper understanding of the possible consequences. This approach enables models to not only understand what they generate, but also why it is safe or ethical. Core principles of deliberative alignment. Explicit safety training. Models are trained on data containing interpretations and explanations of human safety rules, enabling them to better understand and apply these rules in real-world scenarios. For instance, a model may analyze a query, identify potential risks, and avoid generating harmful or unsafe content. Chain of thought, COT. Unlike traditional models that often treat queries as single, isolated tasks, deliberative alignment involves step-by-step reasoning. The model first breaks down the problem into stages, checks it for safety compliance, and only then generates a response. This process helps avoid surface-level answers and fosters more responsible, context-aware analysis. The provided image shows an example of chain-of-thought reasoning used in the training of language models. In this case, the model analyzes an encoded request, interprets it, and explains why fulfilling the request violates OpenAI's security policy. The user sent a request encoded using ROT13, a simple cipher. The request is related to providing instructions on methods that could break the law, e.g., evading detection by law enforcement. The model decodes the message to understand its meaning. After decoding, the context and content of the request are analyzed. Given OpenAI's rules and policies, the model recognizes that the request involves potentially illegal activity. The message is interpreted as an attempt to bypass rules or conceal illegal activities. The model explains why fulfilling the request contradicts OpenAI's security policies, including requests for instructions to carry out unlawful actions. The model refuses to fulfill the request in adherence to policies, even if the user tries to obscure the intent through encryption. This example demonstrates how chain-of-thought reasoning enables the model to justify its decisions step by step, follow predefined rules and security policies, detect attempts to deceive the model. This approach enhances the model's reliability, helping to avoid providing harmful or illegal instructions. Chain-of-thought reasoning allows the model to explain rejections of requests, making its actions more transparent. Adaptability and self-improvement. In contrast to traditional models, which require constant updates, deliberative alignment allows models to adapt to changes in safety and ethical requirements without the need for retraining. This greatly reduces both time and resource costs while enhancing model flexibility. The image presents 4 approaches to training and operating language models, aimed at improving their alignment with safety policies and the quality of their responses. Here is an explanation of each approach. RLHF, reinforcement learning from human feedback. Training process. A prompt is given to a human, who is asked to provide a response or indicate a preference. These data are then used to train the model. During inference, the user sends a prompt and the model generates a response. Features. Training is based on human feedback. Content policies are used to ensure safety. RLAIF, reinforcement learning with AI feedback. Training process. Instead of a human, another model analyzes the prompt based on a constitution, a set of rules that govern how the system should behave. The model's responses or preferences are recorded as training data. During inference, works similarly to RLHF, but the rules are predefined through the constitution. Features. Reduces reliance on human intervention. Uses artificial intelligence for analysis and improvement. Inference time refinement techniques, e.g., self-refine, training process, similar to RLHF. During inference, the model generates an initial response. The response is then refined through additional prompts, refining prompts, that are sent back to the model for further improvement. Features. The model improves its responses dynamically during inference. This approach allows for real-time enhancement of quality. Deliberative alignment training process. A reasoning model is used to analyze the prompt, match it with a set of rules, specification, and generate a chain of thought, COT. These data serve as the foundation for training. During inference, the model reasons based on the trained data and generates a justified response based on the COT. Features. The most complex and advanced approach focuses on transparency and reasoning behind responses. Comparison of approaches. RLHF and RLAIF both rely on feedback, but RLHF depends on human feedback, while RLAIF uses another model. Self-refine introduces the ability to improve responses in real time. Deliberative alignment emphasizes logical justification and transparency of decisions. These approaches help make models safer, more adaptive, and capable of generating high-quality responses. The images illustrate the process of training a language model using SFT, supervised fine-tuning, and RL, reinforcement learning, methods aimed at aligning the model with safety rules and improving its performance. Overall process structure. SFT data generation, creating data for SFT. Safety specifications, spec, and prompts with examples of safety categories. SFT prompts are used. A dataset is generated consisting of 3 parts: prompt, the input query, QOT, chain of thought. Output, the response generated by the model. These data are filtered using a reward model, GRM, which checks the response for alignment with safety policies. The final data form the basis for training the model, GSFT. SFT, e-training. The model is trained using the filtered data, SFT data. The goal is to teach the model to generate a chain of thought, COT, that aligns with safety specifications. RL training. At this stage, the GSFT model is used to generate responses. The reward model, GRM, evaluates these responses for compliance with policies and provides a reinforcement signal. This signal is used to further fine-tune the model to improve its alignment with the specifications. Key elements of the process. Specifications. Spec. A set of predefined rules and safety categories that the model must comply with. Reward model, GRM, filters data and evaluates responses, helping to improve the model's performance. Chain of thought, COT, allows the model to explain its responses, making them more transparent and justified. Final model, G-Spec, At the final stage, the G-spec model, aligned with safety rules, is used for real-world tasks. It demonstrates reasoning ability and the ability to provide responses that align with ethical and policy requirements. This process highlights how modern training methods help create safe and reliable language models capable of handling a wide range of queries while adhering to predefined rules. The graph presents the safety evaluation results of various language models, including O1, GPT-4o, Gemini 1.5, and Claude 3.5, with an emphasis on their ability to refuse malicious queries, jailbreak prompts, and correctly handle harmless ones. Axis description, y-axis, over-refusal accuracy, the level of accuracy with which models avoid over-refusing when processing safe queries. X-axis, jailbreak performance, the model's ability to correctly reject malicious queries measured by strong reject goodness. Key results, Model O1. Model O1 and its earlier version, O1 Preview, demonstrates the best results, being at the forefront of the Pareto boundary. It combines a high refusal accuracy for malicious queries with a minimal number of over-refusals for safe queries. Comparison with other models, Gemini 1.5, Flash and Pro. These models show high accuracy on the y-axis but are less effective in handling malicious queries. GPT-4o, positioned closer to the middle, showing balanced but not outstanding results. Claude 3.5, Haiku and Sonnet, shows lower performance on both axes, indicating the need for improvements in both handling malicious queries and correctly processing safe ones. Errors, error bars, the vertical and horizontal lines at each point represent the standard deviation calculated from over 1,000 trials, bootstrap trials. This accounts for variability in model performance. Conclusion: Model O1 sets a new standard in language model safety, showing that an optimal balance can be achieved between rejecting malicious queries and correctly processing safe ones. This success underscores the importance of implementing advanced training and testing techniques to improve AI effectiveness. While other models like GPT-4o and Gemini show decent results, Model O1 stands out for its stability and accuracy. Drawbacks and challenges, high costs and implementation complexities. Like any innovative approach, deliberative alignment has its drawbacks. One of the primary challenges is the high computational cost. Training such models requires significant computational resources and carefully curated data sets, which increases both development time and financial investment. Moreover, despite improvements in reasoning, models may still make errors in complex or ambiguous situations. For instance, in areas involving sensitive social issues such as politics, religion, or ethnicity, the model may not always correctly interpret the context and fail to account for all relevant aspects, leading to incorrect or incomplete answers.